Hi, my name is Steven Nair. My metric number is CD240251. I'm going to explain about the introduction of this experiment. First, spring stiffness. Spring stiffness tells us how strong or rigid a spring is. When we push or pull the spring, it creates a force that tries to bring the mass back to its original position. A stiff spring is harder to stretch, while a soft spring is easier to move. The second one is natural frequency, mass spring system. When the mass is moved and released, it starts to vibrate on its own. The vibration happens at a natural frequency. A stiffer spring makes the vibration faster, while the heavier mass makes it slower. Third one is beam spring system. In a beam spring system, the beam itself also acts like a spring. So the overall stiffness comes from both the beam and the attached spring. The natural frequency of this system depends on how stiff the structure is and how much mass is moving.
Hello, my name is Shashwina. My matrix number is CD240275. Today I would like to talk about the observation that we obtained from this experiment. In experiment 1, we used 3 springs of different original length. The loads ranging from 200 grams to 800 grams were added gradually, and the elongation of each spring was measured after it reached equilibrium. We observed that the longer springs stretched more compared to the shorter ones under the same load. And in experiment 2, we changed the placement of the springs along the beam at 350 mm and 650 mm and measured the natural frequencies. We found that spring position affect the natural frequency, and it has very important to align the spring properly to keep the beam balanced. Also, the pencil on the oscillator had to be tightly fixed to avoid errors caused by unwanted movement. Now I would like to talk about the calculation we obtained from this experiment. For experimental calculation, we measured force, elongation, spring stiffness, and the oscillation time. By counting the number of oscillation cycles, we determined the period which allowed us to calculate the natural frequencies of the system. And for the theoretical calculation, we used parameters such as spring stiffness, beam length, spring position, and beam mass. The beam length was 730 mm and the mass was 1.628 kg. Using the stiffness values we measured experimentally for the 3 springs, we calculated the theoretical natural frequencies, and this helped us to compare the experimental result with theory and check the accuracy of our experiment. As you can see, we have attached the data we obtained from this experiment, and there's the result from the calculation that we obtained, and there's a table that shows all the data there. Thank you.
The force elongation plot for springs K1, K2 and K3 in figure 3 shows that all 3 springs exhibit linear behavior, confirming that elongation is directly proportional to the applied force and that each spring follows Hooke's law. The slopes of the graph, which represent the spring stiffness, vary between the springs, with K1 having a stiffness of 0.65 Newton millimeter, K2 at 1.673 Newton millimeter, and K3 at 3.063 Newton millimeter. Among the 3, spring K3 demonstrates the highest stiffness due to its larger wire diameter of 1.9 millimeter, whereas K1 with the smallest wire diameter of 1.25 millimeter shows the lowest stiffness. These findings indicate that a clear relationship between the wire diameter and spring stiffness, where an increase in diameter results in a stiffer spring. Table 3 summarizes the expandable results for the beam spring system and shows that both the spring attachment location and the spring stiffness have a significant influence on the interval time and the natural frequency of vibration. A longer attachment distance results in a shorter interval time, indicating that the beam vibrates at a higher frequency. This trend is further supported by Table 4, where an attachment distance of 350 mm, increasing the spring stiffness leads to a reduction in interval time, and the same pattern is observed in Table 5 for 650 mm. These observations are consistent with the theoretical relationship that natural frequency increases with square root of k. Overall, the experimental and theoretical frequencies align closely, with only minor discrepancies likely due to human measurement system, errors, slight spring wear, and minor overstressing of the springs during repeated loading. Discrepancies in the results can be attributed to several factors. First, human errors such as inaccurate measurement readings, improper eye alignment with the scale such as parallax error, and mistakes when counting oscillation cycles can affect the accuracy of the data. Second, the apparatus setup plays a role, as components like the oscillator pencil must be properly secured. Any looseness can introduce unwanted motion and distort the oscillation path. Lastly, the conditions of the springs may influence the results. Springs that have undergone repeated use may experience wear, permanent deformation, or reduced stiffness. A spring that is damaged or overstressed will no longer behave ideally, resulting in errors in the calculated natural frequency. Discrepancies in the results can be attributed to several factors. First, human errors such as inaccurate measurement readings, improper eye alignment with the scale such as parallax error, and mistakes when counting oscillation cycles can affect the accuracy of the data. Second, the apparatus setup plays a role, as components like the oscillator pencil must be properly secured. Any looseness can introduce unwanted motion and distort the oscillation path. Lastly, the conditions of the springs may influence the results. Springs that have undergone repeated use may experience wear, permanent deformation, or reduced stiffness. A spring that is damaged or overstressed will no longer behave ideally, resulting in errors in the calculated natural frequency.
Hello, my name is Uma Sateshwaran Analaki Umasankar, and my matrix number is CD240135. Today I'm going to explain about the conclusion for this report. So in the conclusion, the experiment is successfully achieved its objective by determining the stiffness values of spring K1, K2 and K3, which is found to be that 0.65 Newton millimeter, 1.6 Newton millimeter and 3.06 Newton millimeter. These are confirming that the springs with larger wire diameters exhibit higher stiffness. The interval time for the beam spring system was obtained by containing the number of oscillation cycles per grid division on the grid paper, and the results show that the both of the springs stiffness and the spring position along the beam significantly influence the vibration response. Specifically, higher spring stiffness and larger attachment distance produce smaller interval times and therefore higher natural frequencies. Finally, a comparison between the experimental and theoretical natural frequencies, it only shows minor differences, this indicating that the good agreement between both sets of results and validating the accuracy of the experiment procedure.